All right, well, my name is Jamison Langdon. I'm the principal petrographer at Braun Intertec. I'm a consultant by trade, not a researcher. So a lot of times when I deal with these methodologies, I'm trying to get in and get out as fast as possible. A lot of times we don't have a research project in consulting. We just need to figure things out and move on. So this is really geared towards some of the projects I've worked on and using ancillary methods, which is just different ways that we would normally do petrographic analysis to provide information. So the standard petrographic analysis, just basically it's an as-received observations, stereoscopic observations, and polarized light microscopy techniques to get those observations. And that's the core of the petrographic methods. I would never argue against doing those. Anytime you do a petrographic analysis, if you don't have them, you're probably missing something. But been including a lot of ancillary methods. Things are changing in our industry, and we're seeing a lot of changes in a lot of ways that worked before aren't working as well now. So one of those things that we do on the ancillary side is these kind of different methods, I call the sandboxes I've been playing in. The SEM is, you've seen it abundantly, you'll see it over and over again. It's a great technique. Sometimes the speed of analysis isn't sufficient enough for me to move fast, to rent time, to get a sample in the system, just process times. It can slow me down. And petrographic analysis is a slow process. Also, the nice thing about SEM is you can get that point analysis versus the bulk analysis, which is really helpful. X-ray fluorescence, we just saw one on micro X-ray fluorescence, but mostly in the XRF side. You can get some real material characterizations there. I'm a diffractionist at heart, so XRD is at the heart of my soul when it comes to petrography. If I could scan it with an XRD, I'm happy. But it's not always practical. Whoops, go back. Fourier Transform portable X-ray fluorescence is also very helpful to better understand what's going on. I've been playing with that. It's literally a ray gun. Don't point it at anybody. It will cause some harm. But you can get answers in about 60 seconds, especially if it's attached with a LEAP filter, a light element analysis protocol filter. Fourier Transform Infrared is another one I like to play with, and especially attenuated tonal reflectance. That can be point analysis or bulk, and depending on how you set it up, whether it's on a microscope or on the bench. Its twin sister is Raman spectroscopy, if you ask me, and Dr. Garg has given a nice presentation on the use of that. A lot of things you can see, they kind of overlap with one another in what they can see. Laser-induced breakdown spectroscopy is another thing that I've been playing with. It's a nice fast analysis. You can do it right here in the room. You don't need vacuum chambers or anything like that. You can get elemental analysis right here, right now, in 60 seconds or less. UV-vis microspectroscopy is something else I've been playing with. It's just a fun little toy that I've had that I have not fully utilized yet. And then we have X-ray computed tomography that I've been playing with as well. So in the first case here, we had a piece of stucco that was causing corrosion almost instantaneously after application. And it was really kind of odd because you shouldn't be doing that right away. Here's a control sample. This is what it was supposed to look like. We move over, and we actually have some corrosion products developing. And this was happening around the windows. So water was getting in and causing corrosion, but at a faster rate than should possibly happen. So I did the fun thing, and I whipped out my portable X-ray fluorescence, ground things up, and I was playing with it, and I noticed that the low-rate detector, it has a software that built into it for the chloride side analysis. And usually my number comes out at 1250-ish parts per million, or 0.125%. But when I'm close to that value, it tends to drop to 1,000 parts per million. So, and that's exactly what happened. It went down to 1,000 parts per million approximately on the detection limit for the software. That just picked my ears up and said, let's run a chloride by C1218, water-soluble chloride. And we find out that indeed we actually have 0.1% or 1,000 parts per million of chloride, which if you factor that in a percent by binder, you're looking at about 1.5%. So is there any shock that we are corroding the mesh here? No, we're not. But the PXRF actually allowed us to make a pivot real quick to run the chloride to get an answer of what's going on in real time. So we could also take a piece of that galvanized coated mesh and submit it to SEM&S for metalographic analysis. Great way to find things out. But one of the things I wish I had at this point in time was a lib system, because I can actually, with those systems, scan these pieces and look for that zinc coating on the surface, that sacrificial zinc. Obviously, in the right image is the worst case, it's gone. But also, the libs also gives you a wonderful technique of doing tunneling, where you can keep zapping the same spot over and over and bury yourself into and find out where that zinc is gone, which provides some nice information to the evaluation. So switching on to calcium sulfates, we do those a lot. We have gypsum and hydrite here in the scan, which is we use quite frequently in our industry. One thing that they're the same basic element, the calcium sulfate. One has water, gypsum, 2 water molecules bonded to it, and hydrite does not. And if you put that on the ATR, attachment of the FTIR, you can see 2 very distinct sections. At 3400 roughly, we have distinct peaks going on. That's your water molecules bonded to it. And then we have, at 1100, the sulfates. And it doesn't matter which one you are on, it's telling you it's telling you sulfate's present, whether it's hydrated or not. And why does Raman work? Because Raman does the exact same thing. It tells you over there, the green arrow is sulfates are present. Water is present. So you can do some rapid identification of what's there. In these 2 examples, the analysis is like 60 seconds. You get that scan. And to get that information in that time frame is great. So if you switch over and switch the cations around to say, let's give it epsomite, which is a magnesium sulfate, and the gypsum, which is a calcium sulfate, and this lab stock of sodium sulfate that's been dehydrated, we can look at these and see the sulfates hanging out around 1100 again, green arrow, but we can see the blue arrows pointing to the hydrates, the water molecules bonded to it. Now, epsomite is 10 water molecules bonded, so it creates this great big hump. So you can get this information to try and understand whether there's hydrated phases or not, sulfonated phases or not. Great for doing that. Most of the FTIR work is organic in nature, but you get inorganic signals as well. So let's put this in the field. So in the secondary deposit that was underneath the slab, that was undergoing a tremendous amount of distress. It was turned to mush. So this is a plain polarized light stereoscopic image of what that looked like. Here's the cross-polarized light of what that looks like. That took days for me to get because it was so soft and hard to prepare. It was not an easy step, but we needed it for the photos. The FTIR on the ATR attachment, we can go through and scan that real fast, and we see very clearly we got a blue arrow over there pointing to the water peak. We have water. Over there we have, in green, we have our friend at 1100, the sulfate peak, and a new guy at 1400, which is your carbonate peak. So we have something that has water bonded to it, sulfate, and carbonate. And that is thomsite. So what took me days to prepare, I could get a good reference understanding in like 60 seconds. In 60 minutes, I could take that same product, put it through the XRD, which I will, as I told you, love, and find out that white deposit is thomsite and get the actual mineralogical makeup. And that's a type of orthogonal analysis that we do quite frequently if we can to verify what we're seeing. Coming at it from multiple different angles to confirm what we're seeing. And this is another time when I was playing with a densified slab. It's an interior slab on grade. There's nothing crazy about it. But I wanted to play with that lib system a little bit more. So whenever you see this, you'll see this densified, you'll see the paste color change between the top surface and the down below. So you can see a change in color between top and bottom. It's the same slab of concrete, literally just one's at the surface, one's an inch down. But with the libs, I can go and start zapping around, and on the left is that densified paste. You can see how tight those residual Portland cement clinkers are together compared to down below. We had a blue dye in the image on the right as well. It's kind of throwing your eyes off, but you can see the dispersion change. Down below, it's still a 0.40 water cement ratio, but up above, we're looking at sub 0.40, which is what we see in densified slabs. Now that libs, you can just go around and zap and tell me the chemical analysis in that zone. Give me an elemental map. if you will, at that point. And what it actually clearly showed over and over again, wherever I moved around, we saw an uptick of the available alkalis and iron on the surface compared to what we found at depth. And all that was done in literally a matter of, I figured this all out in about 30 minutes with my playtime. And it was all pretty much there. But I'm lying about the size of the dot. The instrument actually shoots that dot. So, oops. So you have to move around a lot because the dot is smaller than the original Portland cement clippers because you could technically hit it. So you got to get an average moving around. So I also played a little bit recently with X-ray radiography, just like you take it and break your bone, go take a scan. In this particular case, it was a foundation that had a pipe in it, and it was supposed to be grouted. And they were having multiple instances of water intrusion on these sections. They extracted cores out of it, and what you can see in the radiography, you can see the steel right there, very bright on the left, two orientations, and then a hollow area in between, or a change in density in between. And the reason why this is kind of funny is I was actually talking to my wife prior to making this PowerPoint presentation, and we were watching a detective show, and they'd scan the body with the X-rays so that they could prove that nothing was damaged prior to the autopsy. And I told my wife, that's exactly what I do. So that's an example of it, so that when we actually cut it open, we can see they did not grout it. There's just stuff on the end. So it would prove before I even cut into it that there was nothing there. Another little radiography, little experiment is to take a sample, and a lot of times when I do the radiography, it's a sample and then rotate 90 degrees, make my cuts more informed before I make them. And so that's what I did here. Just basically take the sample and rotate it so I can make the perfect cut and get that perfectly sectioned. So that's kind of old tech. We originally obtained a North Star imaging system that does computed tomography. So we can actually take a flexural beam and put it in there. This one has steel fibers in it. And we can just keep making slices all the way through it. Once we have the slices, we can make a three-dimensional model of it. And I can say, please take away the concrete. And keep on stacking it. And so on and so on. So we could literally scan a flexural beam with steel fibers in it prior to actually running the test. Now it's kind of a play box technique. We're just playing around with that. I thought that's going to be somewhere I'm going to use that. So we can do that on both samples in the lab for just general testing purposes, but also in physical constructional elements as well. So we'll just point out the standard petrographic microscopy is at the core of petrography. I would never argue it against the standard C856 protocol, where we basically just kind of look at color changes, size, features present, distribution of features, cracks, whatever, location of deposits if they're there. But these ancillary methods are really just geared towards accelerating, accentuating, and then augmenting our petrographic analysis so that I can go to the engineer and say, look at all these other things and do it faster, quicker, more efficient. Because a lot of times the timetables are kind of tight to get the, especially when construction projects where they're stopped. And that's all I really had. I just want to get you a quick tour of where sandboxes are.